Hello again. After having done SOP, sum of product, form of Boolean expression, I'd like to cover now, still being in chapter 4 in Boolean algebra and logic simplification. I'd like to cover POS, form of Boolean expression, which is a product of sum. So I'd like to show how to convert the Boolean expression into a product of sum, relation between the truth table and Boolean expression, and then using Carnot map to simplify Boolean expression. I'd like to mention here the name Claude Shannon, who was the first who applied Boole's work for logic circuits. In 1938, as his master degree work, he defended his thesis at MIT. So product of sum, easy to guess that when we have sums, Boolean expression in the form of sum, and then when we multiply all of them, create a product of all of them, we obtain the product of sum. And here you have examples, not a plus b multiplied by a plus b plus c, and so on. Please still remember that the single overbar cannot extend over more than one variable. But certainly we may have overbar applied to single variables. So not a plus, not b plus, not c is okay, but a plus b plus c not is not a part of POS format. Obviously we can do it, it's legitimate operation, but it's not a part of POS. If we like to implement the POS to the hardware, according to the rule priority rules in mathematics, when we have product of sum, we perform first whatever there is in the brackets, and then we calculate the product. So going from left to right, we first have the OR gates, and finally at the rightmost position we have an AND gate. And figure 424 shows how to create hardware out of POS expression. As it was in SOP form, we have a standard POS form. So you remember that the standard refers to the number of variables in the prime expression. In SOP, it was a number of variables in product and products. Now, when it comes to sums, the standard POS form requires that every sum includes all variables. So when we have a domain in this example of 4 variables, A, B, C, and D, the standard POS form requires that all 4 variables appear in a sum, which is not the case in this example because the first sum is A plus not B plus C, D is missing here. Then in the second sum we have A plus B plus not D, and C is missing. The fourth, the last sum is in the standard form, but the whole expression is not because we are missing variables in some sums. In certain sums. So the standard POS expression is one in which all the variables of the domain appear in each sum. So when we don't have such a standard form, the question is how to convert the POS to standard POS form. The solution is in the rule 8 of Boolean algebra, which says 8 times not 8 is 0. What does it mean? Because it is 0, we can add up such an expression to any sum without changing its value, arithmetical value. And then after having such an extra product term, we can use rule 12 to expand it into the form of product of sum. Let's have example 417, and in the POS form, it's not in the standard form because the first sum is missing D, second is missing A, the third one is okay, it is in the standard form. So let's take a look on the first sum in which D is missing. So we convert, we expand as A plus not B plus C into A plus not B plus C plus D times not D, which is 0. Now applying the rule 12, we expand this expression into A plus not B plus C plus D, brackets, times the same A plus not B plus C plus not D. And this is the way we artificially introduced a missing variable to the expression. In the second one, the second sum, we are missing A. We do the same, we add A not A. The first one is okay, so finally we have, on the bottom, we have what we needed, right? We have the standard form because every sum contains the whole domain of the expression A, B, C, and D variables. And now, before we come to Carnot and truth tables, it's interesting to find out when the binary value of sums is 0. So, for instance, when we have A plus B plus C plus D, this sum is 0 if and only if all A, B, C, and D are equal to 0. Slightly different is the situation in second sum when we have negations. So we have A plus not B plus not C plus D. The values of A, B, C, D which make this sum 0 are 0, 1, 1, and 0, because not 1 is 0. Very similar way, not A plus not B plus not C plus not D is 0 if and only if all variables are 1. Now the question is how to convert well-known SOP to standard POS. Okay. One moment. And here we are. Example 421, okay? Converting POS to a truth table format, or even converting SOP to POS. So if we have SOP form, for instance, in table 4.6, so we have not A, not B, C, plus A, not B, not C, plus ABC. So this is SOP form. So now we remember that those not A, not B, C is equal 1 when A is 0, B is 0, C is 0. So the combination is 0, 0, 1. In another row, A not B not C is 1 when A is 1, B and C are 0. So we combination is 1, 0, 0. And the last combination for making ABC1 is 1, 1, 1. In order to create now POS, we have to find out what are other combinations of ABC. So we are missing here. So we have 3 combinations. because we have 3 variables, we have 8 possible combinations. So 5 combinations are missing. Which are missing? 0, 0, 0, 0, 1, 0 in the third row, 0, 1, 1 in the row number 4, and then in row number 6 and 7 we have 1, 0, 1 combination and 1, 1, 0. Now when we assign to those combinations the following values. If A, B, and C are 0, to create a sum which is 0, we have to assign variables A plus B plus C. Okay, so here we can write down A plus B plus C. Okay, for combination 0, 0, 0, we assign straight variables. Now we have missing combination 0, 1, 0. Okay, so for this combination 0, 1, 0, we assign A plus not C plus not B, sorry, not B plus C. Okay, and here we have to remember that B is negated. Okay, remember A plus not B plus C. So this is the way we now, out of SOP format, which is known, we assign sums which are 0. And all rows in which the output is 0 creates sum for product of sum. But the convention of converting values of variables into their representation is opposite to the convention we've been using in SOP. In SOP, if a variable was 0, we were assigning not A in product term. Here, when the variable is 0, we assign a straight variable A, B, and C. So this is the way we create. And then when we have all rows with POS, we multiply and we have a POS form. Now the question is how to convert POS expression to truth table format. So let's create the truth table for given standard POS expression in example 421. The same rule, when you have A, B, C straight variables, we know that this sum is 0 when all variables are 0. So we write in the row in which we have all variables 0, we write down sum A plus B plus C. The last example here in the row 7, the variables are having values 1, 1, 0. Therefore, the sum term, which means the term for which the expression is 0, so should be not A plus not B plus C, because if we substitute A and B with 1, not A plus not B is 0, plus C, which is 0, the sum is 0. So in SOP, we've been interested in the rows in which the output is 1. Now we are interested in the rows in which the sum is 0, all 0 rows. And please remember that SOP and POS forms are not a negation of each other. This is a very common mistake we make, because they are not mathematical negation, they are complements of the positions of SOP. So if in a certain position SOP appears as 1, POS appears in the rows in which output is 0. So they complement each other, but it's not a negation, mathematical negation of each other. By the way, you can remember that the example for 20 for SOP is exactly the same. So when we have SOP and truth table for SOP, the POS, which describes exactly the same expression, will be made of sums where they are zero in other rows. So this POS exactly describes exactly the same expression as SOP in example for 20. Okay. So now the question is, okay, if SOP and POS describe exactly the same expression, different way, but so the question is, which form do we take to create hardware later on? So the answer is, it depends on the situation. It may happen in extreme situation that there is just one row with SOP, one row in which the expression is equal 1. So we take SOP form, okay? If we have the situation, for instance, in extreme situation, if there is just one row in which the expression is equal 0, we take 0 as good representation of this expression. In general, to make the expression the simplest possible, we take SOP or POS depending which numbers are represented more in the truth table. If you have more zeros, we use the SOP expression, because we have less ones. If we have more ones, we use 0 rows, which means POS, to create hardware simpler because the expression is simpler. It's made just of less sums than ones. Coming back to the Carnot map, please remember that if we have certain number of variables, 2 powers this number creates this number of cells in the Carnot table. Every cell in Carnot table represents one row in truth table, by the way. So the relation between number of cells and number of cells in Carnot map and number of rows in the truth table is 1-to-1. The difference is that Carnot map is representing the expression in a certain more graphical way, while truth table is in gray code order. And again, please remember that even if you use Carnot map, you have to use gray code sequence. So when you go to the column of combinations of variables, here we have the column of A and B. We have the sequence 0, 0, 0, 1, and now is 1, 1, and then 1, 0. So this sequence of codes for variables, combinations of variables, is not weighted binary system order, mathematical order. It is in gray code order, because we want that every row differs from another neighboring adjacent row just for one value of the combination. So between 0, 1 and 1, 0 would be two changes in A and B, because A, which is 0, then is 1, and B, which is 1, then would be 0. So we have two combinations, two changes of combinations in each variable. When you have gray code, a change from 0, 1 to 1, 1 involves just one change of a variable A. So this is a general rule of using gray code in both truth table, if you want to create, well, truth table you don't have to, but in the Carnot table, yes, because the Carnot table, Carnot map is being used for minimization, and the notion of adjacent cells is very important here. So let's take a look on the Carnot maps for POS minimization. how do you map a standard POS expression? So if the expression is not in standard form, you have to modify this expression into standard form. And once we have standard form, you have all combinations of all variables. And now, in the contrary to SOP, whenever sum in POS is 0, we put 0 in corresponding cell. For instance, in this expression, we have the first sum is A plus B plus C. This sum is 0 whenever all variables are 0. So the sequence of bits in variables is 0 after 0 after 0. So in the cell at the address, in quotes, address 000, we put 0. The next sum is A plus not B plus C. This sum is 0 when A is 0, B is 1, C is 0. We look at the Carnot map and we look at the location of 0, 1, 0, and we find in row 0, 1, column 0, we find the cell into which we put 0. The third sum is not A plus not B plus C. So the corresponding variables making this sum 0 is 1, 1, 0. 1, 1 is the row, 0 is the column. In this cell 1, 1, 0, we put 0, and so on. So this is different from SOP. We put 0, so whenever the corresponding sum is 0. And more example for 33. Again, we look for at some component of the product, and we find the sequence of bits which make this sum to have the value 0, and then we put 0 in corresponding cell of the Carnot map. Now the question is how to simplify POS expression using this rule of filling up the Carnot map with zeros, very similar as it was with SOP. So we create adjacent maps. So if we can create a group of 4, we know that we can eliminate certain number of variables, okay? So if it is group of 4, 2 power 2 is 4, so we can eliminate 2 variables. For instance, for the group of zeros in the top, the minimized form of this sum would be just A, because A is 0 and C does not matter, okay? So we have, when we look at the rows, 2 rows, in both rows, A is 0, okay? B is changing from 0 to 1, C is changing from 0 to 1, because this change does not change the value of the sum, we can ignore B and C. So when you have the group of 4, 2 power 2 is 4, we eliminate 2 variables. In this case, we eliminate B, A, C. So only A remains here. Then we have a group of 2. Okay, in the row number second row 0, 1, in the row 1, 1. We have a group of 2, so 2 power 1 is 2, so we can eliminate 1 variable. And you can clearly see that the variable which is eliminated is A for those 2 cells, because A is changing from 0 to 1 or from 1 to 0, and this change does not affect the value of the sum, so we can ignore A. This is why instead of group of 2, we write not B plus C, because B is 1, C is 0. Applying this convention of relation between variable and bits, we write here not B plus C, not B for B equals 1, and C for C equals 0. By the way, on the same Carnot map, you have corresponding SOP. Both describe perfectly correct the expression. You have to remember that when you group and minimize groups of zeros, then you create corresponding sums and you multiply those sums. So in SOP, we've been adding the groups. Here we are multiplying the sum. So the first sum was A, the second sum was not B plus C, and we multiply them. Different from minimizing SOP and creating a minimal SOP expression, we here in minimal POS expression, we multiply. So adjacent cells work the same way as they did in SOP. Number of variables we eliminate correspond exactly to the same. By the way, if all the cells contain 0, which means 8 cells in a group of 8, 2 power 3 is 8. So we eliminate 3 variables. It would mean that the whole expression is always equal 0. We have more examples. And again, we create groups of adjacent cells. For instance, we have a group, horizontal group in the first row. We have cell 0000 and cell 0010 adjacent, wrapping around. So because we have a group of 2, we eliminate just 1. And because A and B and D are 0, we have A plus B plus D. C is changing, so C may be eliminated. Another interesting group is a colon, leftmost colon of zeros at the address CD00. Because A and B are changing and expression is still 0, we eliminate A and B. All which is constant is C is 0, D is 0. So using the convention, we write down straight variables and we add them up. C plus D would be a good sum for this column. Following this way, we multiply then those sums and we have expression as given in this example. Now, interesting question: how to convert SOP to POS. The conversion is very simple because if we start from SOP, we fill up the map with ones, as it is below here. Okay. If we prefer to start with SOP, we start with SOP. We fill up the Carnot map with ones, and then the rest are zeros. So if you want to have the representation of the expression in the POS form, you just take into account the zeros and then minimize by grouping the adjacent cells of zeros. And once you have those groups, you multiply corresponding expression. So this would be all about POS format. Thank you very much.